In the front end of every operational amplifier, there's a differential amplifier. Very, very important part of the circuit. In fact, these differential amplifiers are found in many electronic pieces of circuitry. The differential amplifier can basically be called a common emitter on one side and a common base on the other, because when we put a DC voltage onto the base on this transistor, positive DC voltage, the base goes high. Through emitter-follower action, the emitter voltage also goes high. The emitter is effectively tied to the other emitter on Q2. That emitter goes high in voltage, reducing the voltage between the base and the emitter on this transistor, which in fact turns that transistor off. I'm going to put a DC voltage onto the base of Q1, Q2. I'll put a DC voltage positive onto the base of Q1, and we'll see what happens on the oscilloscope. We can see then that the yellow trace, which was Q1, DC coupled, has dropped. This is 0 voltage in the middle. It dropped by 2 divisions, which is minus 10 volts. The opposite transistor, Q2, has jumped up in voltage by the same amount. So that shows exactly what I was saying. This particular base has gone high. This transistor turned on harder. There was more collector current traveling, therefore the collector voltage fell. The opposite transistor turned off because the emitters are joined together. It's configured in common base. The base is grounded. The input's going into the emitter. Therefore, when the base emitter junction voltage fell, the transistor turned off. There was less collector current flowing, and therefore the collector voltage went high. Let's see that again. Here's Q2 collector, here's Q1 collector. The Q1 collector fall, that's the yellow trace. You'll see Q2 collector rise, that's the blue trace. And of course, if I reverse the situation on these two bases, do that again. This time, because I've got the DC voltage going into the base on Q2, we'll see Q2 collector will fall because there'll be much more collector current flowing, bigger voltage drop across the 22K resistor. The emitters are tied together. This emitter voltage has followed the base. The base goes high when I turn the voltage on. The emitter will also go high through emitter-follower action. The emitter is joined to the opposite emitter, and therefore that voltage going high reduces VBE, turning this transistor off. Let's watch. In this case, Q2 collector went low, Q1 collector went high. One transistor turned on, the other transistor turned off. This is exactly what's happening in a differential amplifier with what's called single-ended input. I have positive voltage just going to one base, and this is differential amplification. Now, I'm going to do something a little bit different. I'm going to show common mode amplification as well. I'm going to tie both the bases together. Here we are, and you can see the DC voltages have collapsed to my 0 volt line in the middle. I'll turn off that DC voltage, virtually no change. Turn it back on again. And what I'll do, I'll even crank that up a little bit more, 4 volts, 5 volts, 6 volts, 7 volts, 8 volts. There's no difference in the output voltage on the collectors because both transistors are working in harmony now. They're both doing exactly the same thing. We have the same voltage polarity going into both bases. This is called common mode amplification. And an ideal differential amplifier, we want extremely low amplification factor for common mode, where we've got identical signal going into the bases, but we want a very high amplification factor for differential mode, which is what I showed first of all with the single-ended input. I'll go back to single-ended again. I change the voltage there. And I think that's a good overview of how our basic differential amplifier functions. Now, in another section of either this video or perhaps the next video, I'll be using an AC signal coming from my function generators going into each base. We'll look at, again, differential amplification using AC and common mode amplification using AC at the same frequency, and we'll try and get the same DC level onto each base. And by doing that, we'll get a better idea of what's happening with this transistor at the bottom, because when the switch is connected this way in this sample board, we've got 22 k ohms of resistance in the emitter circuit, and this way we've got a constant current source which has a very high output resistance, and we're going to find out that using this has an extremely good rejection ratio for changes in the common mode voltage at the inputs in comparison to the outputs.